Good morning. Today our lesson is about experimental probability. So our objective is to understand and use experimental probability to solve problems. Heads or tails. If you have a coin and you flip it, you will get either heads or tails. Suppose that you flip this coin 10 times and you record your results. It can be same number of heads and tails, but most of the time you will get different heads. When I did this experiment, I get 7 heads and 3 tails. This means that the probability of getting heads in my experiment was 7 out of 10 and the probability of getting tail was 3 out of 10. But when we usually say that we have a coin that has two faces, head or tail, the probability of getting each one is 1 out of 2 because we have two different outcomes. The total outcomes is 2 and one head means 1 out of 2. That's why the experimental probability it's different than the theoretical probability. Experimental probability depend on the experiment itself. Tony spins two five-sided spinners, both with sides numbered from 1, 2, 3, 4, and 5. He multiplies together the two numbers landed on. Draw a table to show all possible outcomes. Use your table to find this probability. Probability of getting an even number, probability of getting an odd number, probability of getting a multiple of 3, and probability of getting a factor of 25. First of all, let's draw the table. We will have on the horizontal line the first or the green spinner, which is numbered from 1 to 5, and on the vertical column we have also the another spinner also numbered from 1 to 5. The first one is the product of 1 by 1. So 1 by 1 get 1, 1 by 2 get 2, 1 by 3 get 3, 1 by 4 get 4, and 1 by 5 getting 5. Why I'm multiplying? Because they said for us that he multiplies the two numbers landed on. And we will continue the table. For example, if I take 4 by 4, the answer is 16. And 4 by 5, the answer is 20. So the possible outcomes here are 1, 2, 3, 4, 5, 2, 4, 6, 8, 10, 3, 6, 9, 12, 15, 4, 8, 12, 16, 20, 5, 10, 15, 20, and 25. Probability of getting an even number, we will see which of these outcomes are even. So we have 2, 4, again 2, and again 4, 6, 8, 10, 6, 12, 4, 8, 12, 16, 20, 10, 20. So their sum is 16 out of 25 because we have actually 25 possible outcomes. Probability of odd number, so we will count the odd numbers and they will be 9 out of 25 because all of the outcomes are 25. 16 of them are even, so the rest will be 9 from the 25. Probability of multiple of 3, we have 3, we have 6, we have another 3, we will count it again, another 6, 9, 12, 15, 12 again, 15 again. So the probability will be 9 out of 25 because I counted them and there are 9 possible outcomes. A factor of 24 means what I will multiply by a different number and I will get 24. So we will see the factors. Actually, we know that the factors are 1, 2, 3, 4, 6, 8, and 12, and 24. So if you counted them and if you find them in your table, they will be 14 out of 25. Listing possible outcomes. Usually when you roll a fair dice, you are equally likely to get one of 6 possible outcomes, which are either 1, 2, 3, 4, or 5, or 6. So because we have 6 possible outcomes, each one will have the probability 1 out of 6. And we will check now if we are rolling this dice and we are doing experiment. Will we get the same probability? Let us see. I rolled the dice 50 times and I record my results in a table. The first column I put the dice results, which are 1 to 6, and the second column I put the frequency, means how many times I get each number. From that table, I can see that I get most of the time 4 when I roll my dice, and I get one time only a 1. And I can see from the results that I can estimate the probability of getting 6, which is 1 out of 5, because it's 10 out of 50, and then I will simplify it. The more you repeat your experiment, the more the data is reliable to use or to depend on. Do you think the dice is biased, not fair? Yes, actually, because I didn't get the same number of times for each result. Yeah, for example, I get 1 time for 1 and 17 times for 4. So the answer is yes. After listing the outcomes, when I rolled a dice, my result shows that the number 4 was likely to be the outcome. We got it 17 times. And the probability of each face is 1 out of 50, 3 out of 25 after simplifying, 4 out of 25, 17 out of 50, 4 out of 25, and 1 out of 5. So the number 1 was the least common number rolled. Extension. If you roll the dice 250 times using your probability, how many 6 would you expect? You already found that you have the probability of getting 6 1 out of 5. So if you have to roll it 250 times, you will multiply the probability you're getting depending on your experiment by the number of times. So it is 1 out of 5 times 250. 1 out of 5 is 0.2 times 250 means 50 times. When they are asking you like these questions, do not depend on the theoretical experiment, which is 1 out of 6. Depend on your result. What you get in your result, use it and multiply it by the number of times. Probability or relative frequency. This term is used when we have experimental probability. It's the same as the probability, but now we are depending on the number of times that the event occurs out of the number of trials. So numbers 1, 2, 3, 4, 5, 6. It's a biased die because the frequency is not the same for all the numbers. To find the number of trials, you add all the frequencies. So we have 250 trials. And to find the relative frequency, which is the probability, just divide the frequency by the number of trials and you will get the result. Now, they ask us information to estimate so the answer is 180 times. Get frequency by 1800, it's 245, and so on. All number of times each is equal to 1800. So as a plenary, a bag contains an unknown number of colored discs. Rebecca selects a disc at random from the bag, notes its color, and replaces it. She does this 500 times, and her results are recorded in the table below. Rebecca hands the bag to Peter, who is going to select one disc from the bag. We need to use the information from the table to find estimates for the probability that Peter selects a red disk, the probability that he doesn't select a blue disk, and the number of yellow disks that Rebecca could expect for 1800 trials. From the table, we can find that each color has different number of appearing. So to get red desk, we will take the number of times the red desk appear, and we will divide it by the total number of times Rebecca select the desk. So it will be 200 divided by 500, so it's 2 out of 5, or 0.4, or 40% if you want to find it as a percentage. Of course, the probability we can get it as a fraction, decimals, or percentage. The probability that he doesn't select a blue desk. Getting a blue desk is 8 out of 500. To not get a blue desk, it will be 1 minus 8 out of 500. So it will be 492 times out of 500. You can do it 984 out of 1000 in order to be easy for you to find it in decimals, which will be 0.984, and it's 98.4%. Of course, we multiplied both numerator and denominator by 2 to get it out of 1000 in order to make it easier for us to find the answer in decimals. For C, I need the number of yellow desks that Rebecca could expect in 1800 trials. First of all, let us find the relative frequency, which is 115 divided by 500, and then multiply the answer by 1800. So I have the relative frequency 0.23 multiplied by 1800. The answer is 415 times. Thank you for listening and have a nice day.